Kia ora, and welcome to a lesson on Cambridge Mathematics P2 using iterative process to solve problems. Let's have a look at an example. We've got the equation e to the x minus 1 is equal to 2x, and we know there's a root alpha equaling 0. We're going to show by calculation that this equation also has a second root, beta, such that beta is between 1 and 2. We're then going to show that this equation can be rearranged as x equals log 2x plus 1. And then we're going to finish this off by using an iteration process based on the equation from part B to find a suitable value for beta to three significant figures. Starting off with part A, we're going to show by calculation that this equation has a root beta such that beta is greater than 1 but less than 2. So to do this, you say e to the x minus 1 minus 2x is equal to 0. And you may see this as familiar as a kind of function situation where you try to solve for solutions equaling 0 as a single graph where it crosses that x-axis. So what we can say is this is actually our function e to the x minus 1 minus 2x, and to prove that there's a root between 1 and 2, all you have to do is substitute in the value 1 and 2 and check for change of sign. So f1 is equal to e to the power 1 minus 2 lots of 1, which is equal to minus 0.2817. f of 2 is equal to e to the 2 minus 1 minus 2 lots of 2, which is equal to 2.38905. And as you can see from here, there has been a change of sign. Therefore, a root is present. So we know e to the x minus 1 equals 2x has a root between 1 and 2, as well as a root at 0. Okay, let's have a look at B. We're now going to show that this equation can be rearranged to be x equals log 2x plus 1. So if you've got an exponential question and you're seeing a log thing, that's basically just your standard rearrangement. So go from e to the x minus 1 equals 2x. Well, if you look at this final solution you try to get to, that minus 1 is now plus 1, so it's kind of obvious that that is what we need to do first. So we're going to do 2x plus 1. And then it's, how do you get rid of e to power x? Well, to get rid of the e, you take natural logs of both sides, which leaves you with x on the left and natural log 2x plus 1. So a fairly basic rearrangement. Okay. Part C says using that equation from part B and a suitable starting value, which they've kind of given you with part A, find beta correct to three significant figures. So what we're going to say is xn plus 1 is equal to our previous equation, not the equation we've currently got, but our previous equation, which was x equals log 2x plus 1. So log 2 lots of our xn plus 1. So the next number in the sequence is equal to log of 2 times our current number in the sequence plus 1. It says using a suitable starting point. Well, we know that the root is between 1 and 2. So let's choose a number between 1 and 2 to start with. So I'm going to start off with 1.5. On a calculator, I will type in log bracket 2 lots of 1.5 plus 1. In fact, I'll just write that down. That is what I am doing. So I'm doing log 2 times 1.5 plus 1 on my calculator, pressing equals, and it's giving me the solution 1.3863. Rather than constantly retyping this equation out and changing that 1.5 to the next number, what I'm going to do now is on my calculator I'm going to do log 2 times the answer plus 1. So remember, don't clear your calculator at this point. Replacing the 1.5 with answer means that's going to use our previous value, which is going to give a solution 1.3278. Okay. Now I don't need to change anything in my equation. I can just keep hitting equals till I get to a solution that is correct to 3 significant figures. However, I should write down every single value I get along the way to communicate to the examiner that I am actually working it out properly. So in the question it also told us to write the answer to 5 significant figures. Just pay attention to your answer to 5 significant figures and see what it would round to each time it's 3 significant figures, because that will make a difference. So when I press equals again, I get 1.2962, and then I press equals again and I get 1.2788, equals again gives me 1.2691, equals again gives me 1.2636. It's getting closer now. I can see I'm between 1.27 from my 1.2691 to 3 significant figures and 1.26 to 3 significant figures. Press equals again and I get 1.2605. Well, this to 3 significant figures is 1.26. This is also 1.26 to 3 significant figures. So our solution to 3 significant figures is 1.26. We can then prove that the root beta is 1.26 to 3 significant figures by using our change of sign process from part A and taking the upper and lower bounds, which would round to 1.26, substituting it in and showing that there's a change of sign between those two values. So we're going to do that quickly now. So I'm going to do f is the lower bound, 1.255, which would equal e to power 1.255 minus 1 minus 2 lots of 1.255, which gives me a solution minus 0.0021616, and taking the upper bound, which would be 1.265, and doing e to power 1.265 minus 1 minus 2 lots of 1.265, which gives me a value of 0.01309. Again, this is showing a change of sign, therefore the root must be present. So change of sign indicates presence of root, therefore beta equals 1.26, correct to 3 sig fig. Okay, let's have a look at another question. So here's our second example. This is a trig example, and the examples you get given with these iterative processes tend to not be easily solvable via any method you may have seen before. So that's why we have to use this numerical process of sort of trial and improvement, but a better form of trial and improvement. So for part A, we're going to just show that 1 plus cos x over 2 sin x when squared plus 1 minus cos x over 2 sin x squared is equivalent to cot squared x plus half. So this is just using trig identities. So we're going to say we're going to expand out the squareds to get 1 plus 2 cos x plus cos squared x over 4 sin squared x plus 1 minus 2 cos x plus cos squared x all over 4 sin squared x. We're going to combine our two fractions together to get 2 plus 2 cos squared x over 4 sin squared x. Okay, at this point I would look at this and see how is this related to what we've got up above. I can see where the cot squared x is going to come from. I've got a cos squared divided by a sin squared. But how's a half going to occur? Well, that's only going to occur by having some form of cancellation with sin squared x. And the only other thing that I've got here is the 2. So I have to think, how can I get 2 into a sin squared x form? And that is by saying, well, if 1 is equal to sin squared x plus cos squared x, then 2 must be equal to 2 sin squared x plus 2 cos squared x. So I'm going to replace the 2 here, which is going to give me 2 sin squared x plus 4 cos squared x, because I'm adding an extra 2 cos squared x on, all over 4 sin squared x. Now you can see how this is going to split. So 2 sin squared x over 4 sin squared x plus 4 cos squared x over 4 sin squared x. Sin squared x is going to cancel out. 2 over 4 simplifies to a half. Cos squared over sin squared is cot squared. 4 divided by 4 is 1. So plus cot squared x. There we go. We've shown how this becomes cot squared x plus a half. Let's have a look at the next part. Hence, given that alpha is a root of the equation of what we just showed equals x, show that alpha is also root of equation x equals the inverse tan root 2 over 2x minus 1 for 0 at x is greater than 0 but less than pi over 2. So whenever there's one of these hence questions, you never actually use the starting point that they give you, the starting point. You always use the point that they told you to prove a second ago. So we're going to say cot squared x plus a half is equal to x. I'm going to get rid of a half by timesing through by 2 to give me 2 cot squared x is equal to, plus 1 is equal to 2x. Take the plus 1 to the other side to get 2 cot squared x is equal to 2x minus 1. Then I'm going to think about what 2 cot squared x means. Well, 2 cot squared x means 2 over tan squared x, which is equal to 2x minus 1. I'm going to do a quick flip around to go 2 over 2x minus 1 equals tan squared x. So tan x would be the root of 2 over 2x minus 1. So x would be the inverse tan of root 2 over 2x minus 1. Proven. Now let's have a look at our next question, our next part. Part C says it is given that alpha is the only root of the equation x equals the inverse tan root 2 over 2x minus 1 for x is greater than 0 but less than pi over 2, and we're going to verify by calculation that the value of alpha lies between 0.9 and 1. So this is similar to our first example. We're just going to do a rearrangement of this to find a function x and then substitute in 0.9 and 1 to show that there's a change of sign between these two values. So what we're going to say is that x minus the inverse tan of root 2 over 2x minus 1 is equal to 0, which again, making it equal to 0 is like saying this is our function and where it crosses the y-axis is what we're interested in. So our function x is x minus the inverse tan root 2 over 2x minus 1. And we're going to try the values 0.9 and 1 in here. So simple substitution question. F is 0.9, therefore we've got 0.9 minus the inverse tan of root 2 over 2 lots of 0.9 minus 1, which gives you the value. Just check the value. The value is minus 0.10685 minus 0.10685. And then we're going to do f is 1, which is 1 minus the inverse tan root 2 over 2 lots of 1 minus 1, which is equal to 0.44683. Okay, so change of sign. Indicates presence of root. Okay, let's have a look at how this follows into part D, which is using an iterative formula based on the equation in part C, find the values of alpha correct to 3 significant figures. Well, we know alpha is between 0.9 and 1, and we have equation x equals the inverse tan. So our iterative formula is going to be written x n plus 1. The next value of x is equal to the inverse tan of root 2 over 2 lots of our current x value minus 1. Okay. Same thing as on example 1. We're going to choose a value which makes sense. So we know it's between 0.9 and 1. So I'm going to start with my first x value of 0.95, something in between. I'm going to type that into my calculator. Again, I'm going to write down what I'll type in my calculator. I'm going to do the inverse tan of root 2 over 2 lots of 0.95 minus 1 on my calculator. And that gives me the solution 0.97992. 0.97992. Okay, this is not correct for 3 significant figures currently, so I need to do the process again. But instead of typing it into my calculator again, I'm just going to go back into what I've already typed and change the 0.95 to answer. So now when I press the equals, it's going to use the previous value every time. So the next value it gives me is 0.96494. Press equals again, it gives me the solution 0.97234. Still not correct for 3 significant figures, so I'm going to press it again and it gives me the value 0.96866. Again, not correct for 3 significant figures. Again, 0.97048. Getting a bit closer now. 0.6866 and 0.7048 are very close in terms of 3 significant figures. Going to press it again. I get the value 0.96958. Well, to 3 significant figures, this is 0.970. To 3 significant figures, this is also 0.970. So 0.970 seems to be the correct solution for alpha. So alpha seems to be 0.970 to 3 sig fig. Now to just test that, to find out whether that is actually true, I'm going to take the upper and lower bounds of 0.970 and put it into our function that we were playing with earlier. So we're going to say the lower bound of 0.970, which is 0.9695, is equal to the x minus the inverse tan that we did, sorry, on the last one, x minus inverse tan 2 over 2, root 2 over 2x minus 1. So 0.9695 minus the inverse tan of root 2 over 2 lots of 0.9695 minus 1, which gives me a value of minus 571, and then f of the upper bound, which is 0.9705, is equal to 0.9705 minus inverse tan root 2 over 2 lots of 0.9705 minus 1, which gives me a solution of 0.000924. Again, we have this change of sign situation, which indicates the presence of a root. So we're going to say change of sign indicates presence of root, therefore alpha is equal to 0.970 correct to 3 sig fig. Okay, hopefully that made sense and you can get your head around some questions now. Good luck, and I'll speak to you again soon.